Right, so now that definite integrals of functions of a complex variable have been defined, we can go straight to contour integrals. And the idea is that complex functions of a complex variable are really usually integrated along parametric curves, and the integrals are ultimately reduced to integrals of complex functions of a real variable as introduced in the previous presentation, which means that we've got all the tools needed to get going. First of all, we want to talk about these contours. And basically, if we've got a set C of points x, y in the complex plane, remember that the point x, y is equal to the complex number x plus iy, right? That set of points is called an arc if and only if there are continuous functions x of t and y of t with a smaller or equal t smaller or equal b, so that for every x, y, and c there is a t, so that x is x of t and y is y of t. So that's basically a parametric curve as you know it from calculus. And what you can do with those things is, well, you can just basically as t varies, x of t and y of t traces out a curve, and you can pretty much draw any curve you want with that. We call that thing C, and typically then x of a, y of a is the starting point, and x of b, y of b is the ending point of that arc. Okay, so again, with the usual switching between two-dimensional notation and complex notation, we can also write the continuous function as z of t being x of t plus I y of t. And well, an arc is called a Jordan arc or a simple arc if and only if for t1 not equal t2 we have z of t1 not equal z of t2. You remember in the previous picture, those loops, basically the curve intersected itself. In a Jordan arc, you don't have these self-intersections. You just go from the starting point to the ending point, and you don't have anywhere where the curve comes to the same point twice. An arc then is called a simple closed curve if, except for the fact that the starting point is equal to the ending point, we have that t1 not equal t2 implies z of t1 not equal z of t2. So that means we've got an arc, and that arc closes back up no matter how crazy it acts, as long as it doesn't self-intersect except that the starting point is equal to the ending point. That's a simple closed curve. And then a simple closed curve is called positively oriented if and only if it is traversed in the counterclockwise, which is the mathematical positive direction. So that would be something where we go around the arc in this fashion. Since we've got a parameter t that grows, there really is a direction always associated with the curve, and the counterclockwise direction in which we traverse the curve, that's the mathematically positive direction. An arc is called smooth if and only if the function z of t that traverses C is differentiable with continuous derivative and z prime of t not equal 0. So that means this arc that we talked about at the beginning, that one actually is smooth. It doesn't have any corners. But something like this, if I were to replace this part with that, that is not allowed. Basically, a smooth arc, geometrically speaking, is something that doesn't have any corners. Okay, an arc is called a contour or a piecewise smooth arc if and only if it consists of smooth arcs joined end to end, and it's called a simple closed contour if and only if there is no self-intersection except that the initial point equals the final point. So this corner, that is okay for contours, and that's important because we ultimately will want to do contour integrals over squares and things like that, and that means that corners have to be allowed somehow, and we do that by allowing the arc to be pieced together, basically. Note that this one then, of course, is not this contour is neither simple nor closed because it has a self-intersection, and the starting point and ending point are different from each other. Okay, if we set z of theta being e to the I theta and let theta go from 0 to 2 pi, then the unit circle, which is the set of all complex numbers so that z absolute value is equal to 1, that's a positively oriented simple closed curve, and that's because, well, as theta increases, we know that e to the I theta is the complex number that is here with the angle theta being between the positive x-axis and the position vector of the point, and as theta increases, we're going around the circle in the counterclockwise direction, which is the positive, mathematically positive direction. When z of theta is e to the negative I theta, and theta goes from 0 to 2 pi, then it's a simple closed curve, but it's not positively oriented because this time around, well, negative theta goes in the opposite direction, and so we're going around the circle in the clockwise and mathematically negative direction. Okay, the length of a contour that is parameterized by the function z of t, that is just L equals integral from a to b z prime of t absolute value. Well, that's just something, you can't prove a definition, but you can certainly discuss it a little bit. And if the length is given by this formula, we remember with z being x plus iy, we have z prime absolute value is the square root of x prime squared plus y prime squared. And that is the length formula that you have seen in multivariable calculus for parametric curves. And so again, that means that what we're doing here is geometrically consistent with things that we've done for functions of real variables. If we now have a continuous function of a complex variable and see a contour that's parameterized by z of t, then we define the contour integral of f over the contour c as integral c f of z dz, being the integral from a to b of f of z of t z prime of t dt. So we just plug in the parametrization of the contour into the function. That way the function only is evaluated on the contour, and then we multiply by z prime t dt because that's basically a small step on the contour. Now note that if phi is differentiable with continuous non-zero derivative and maps alpha beta to the interval ab, well then z of phi of tau is another parameterization of the same curve c. It just uses the parameter tau in the interval alpha beta rather than the parameter t in the interval ab. But the integral of f over c is not affected by interchanging the parameterizations in this fashion. And that's because if we set xi, that's the first time we see the Greek letter xi, I think, well, xi is just a strange squiggle if I put it on the board. Xi of tau is z of phi of tau, and if we have that, then we have that the integral from a to b, f of xi of tau, xi prime of tau d tau, well, that's the integral from alpha to beta, f of z of phi of tau, because that's what xi is, and xi prime is z prime of phi times phi prime, which is what we have here. And now we use a substitution, which will be t equals phi of tau, and then dt d tau is phi prime, so we get that this thing here is dt. And so that means this is the integral from a to b, f of z of t, z prime of t. And that's how the contour integral was defined to begin with. So that means that the definition of the contour integral is sensible as an integral that only depends on the contour. It only depends on the shape. It doesn't depend on the way we parameterize it. And that's very important because we want these things to be, in the end, geometric entities that don't depend on how fast we go around the contour. We omitted the proof here that any two parameterizations differ by a function phi as described, and that is a very technical part that I would recommend a class in real analysis for example. Okay, what rules do we have for contour integrals? Well, scalars can be factored out just as before, so if you integrate wf of z, then that's w times integral of f of z, if w is a complex number. The integral of a sum is the sum of the integrals, and if negative c is the same contour as c only traversed in the opposite direction, then basically z of negative tau with negative beta smaller or equal tau smaller or equal negative a is a parameterization of that contour. And the integral of negative c f of z dz is the integral from negative b to a, z of negative tau dd tau, z of negative tau, just by definition. Remember, the prime always is with respect to the variable, so the variable is tau here, so that's the dd tau. Compute that, we get the integral from negative b to negative a, f of z of negative tau, z of negative tau, z prime of negative tau. Okay, now we have the z prime of negative tau times negative 1, so that's the derivative of this thing with respect to tau. Now we do a substitution, t equals negative tau, which means we get the integral from a to b, f of z of t, z prime of t, and the negative 1 d tau, that's the dt. And of course, that's just negative the integral over the contour c f of z dz, because the only difference is that the bounds of the definite integral have been flipped. Okay, if the endpoint of one contour c1 is the starting point of another contour c2, then the union of the two contours is c1 plus c2, and we have that the integral over c is the sum of the integral over c1 plus the integral over c2. That's the contour integral analog of just splitting an interval somewhere in the middle and then getting that the integral over the whole interval is the sum of two integrals over subintervals. Okay, examples. Well, let's compute the contour integral of f of z equals z absolute value around the upper half of the positively oriented unit circle. Well, that's the integral f of z dz, which is the integral from 0 to pi of z absolute value with a parameterization, which is e to the it with t from 0 to pi plugged in, times the derivative of the parameterization, I e to the it dt. E to the it absolute value, of course, is 1, so that's just the integral from 0 to pi e to the I times e to the it, and the antiderivative of that is e to the it in the bounds from 0 to pi, which turns out to be negative 1 minus 1, which it should be, and because that's the upper bound, yeah, e to the I pi minus e to the 0, which is negative 1 minus 1, which is negative 2. Tried to compute a little too fast here. Okay, theorem. If our complex function has an antiderivative capital F of z, then the integral of f over the contour c parameterized with z of t, t going from a to b, is equal to the value of the antiderivative at the endpoint minus the value of the antiderivative at the starting point. So this is sort of like a fundamental theorem of calculus for contour integrals. And the proof goes through the fundamental theorem of calculus. We take the integral f of z dz, which is the integral from a to b, f of z of t times z prime of t, and that's just f of z of t from a to b. Hang on just a minute here. Okay, yeah, I was talking about the fundamental theorem of calculus, and then it looks here like we're using the fundamental theorem of calculus. Well, that's because we do. We did prove in the preceding presentation that for integrals of complex valued functions over intervals, the fundamental theorem of calculus works out, and the antiderivative of f of z of t, z prime of t, is capital F of z of t, so that is in the bounds a and b, and that's of course f of z of b minus f of z of a, just as we claim here. So that one rests upon a theorem that we've already proved, and the argument is quite simple. Okay, so if we have a complex number n, and let's be very careful here, even though n usually is used for integers, we let n be a complex number this time, and we want to integrate the function f of z equals z to the n around the positively oriented unit circle, which is something that we'll actually have to use quite a few times. Well, then the integral over the unit circle of z to the n dz, that's the integral from 0 to pi, parameterization, which is e to the it plugged into z to the n times the derivative of the parameterization, I e to the it. Well, that's integral from 0 to 2 pi I e to the I times n plus 1 t. And that's the antiderivative here is 1 over n plus 1 e to the I n plus 1 t from 0 to 2 pi. The easiest way to see that something is an antiderivative is to just take the derivative, and it does work out. And that is for n not equal to negative 1, right? Because we can't divide by 0. And for n equal to negative 1, the integral over c of z to the negative 1 dz is the integral from 0 to 2 pi of I. Whoop. Well, that actually is not a typo and not something that I would need to stop for. When n is equal to negative 1, we get that this exponent here is 0, and that means all that remains is the integral of I, and that's 2 pi I. In particular, now, that means that when n is an integer that is not equal to negative 1, then the integral is 0, because what we get is e to the I integer multiple of 2 pi, which is 1 minus e to the 0th, which is 1 also, and so that would mean that that integral turns out to be 0. Note that even though we had to be very careful with branches, this all works out in fact, for complex exponents, and that is, well, for integer exponents there is no problem because there is no ambiguity, but for complex exponents the computation is not affected that we're crossing a branch cut. We just basically stay with a branch, we choose a branch, and as long as we stay consistent with that branch as we go along the integral, and that's what we have to do, then things will not be a problem, because a value at a single point where the power function may be discontinuous, that value will not affect the integral. And with that, we have talked our way into contour integrals. So anytime we have no other opportunity but to directly evaluate a contour integral, we basically go back to calculus. We take the real part, we take the imaginary part, we compute antiderivatives. But it turns out that a lot of complex analysis now revolves around the computation of contour integrals by other means, as well as the estimation of contour integrals, because sometimes we will need to let these contours grow to infinity and somehow show that the limit of those contour integrals exists and typically is 0. Which means why, and this is why in the next presentation we're going to talk about estimating contour integrals. So after we've talked about in the last presentations algebra, trigonometry, as well as calculus, now we're going to go back into the advanced mathematics part, if you will. Estimation is the kind of thing that we typically don't do that much in calculus, but we're back with it, and we'll talk our way through those inequalities, and you'll be on top of them then. All right. Right, so now that definite integrals of functions of a complex variable have been defined, we can go straight to contour integrals. And the idea is that complex functions of a complex variable are really usually integrated along parametric curves, and the integrals are ultimately reduced to integrals of complex functions of a real variable as introduced in the previous. And well, an arc is called a Jordan arc, or a simple arc if and only if for t1 not equal t2 we have z of t1 not equal z of t2. You remember in the previous picture, those loops, basically the curve intersected itself. In a Jordan arc, you don't have these self-intersections. You just go from the starting point to the ending point, and you don't have anywhere where the curve comes to the same point twice. Draw any curve you want with that. We call that thing C, and typically then x of a, y of a is the starting point, and x of b, y of b is the ending point of that arc. Okay, so again, with the usual switching between two-dimensional notation and complex notation, we can also write the continuous function as z of t being x of t plus I y of t, and x of t and y of t with a smaller or equal t smaller or equal b, so that for every x, y, and c there is a t, so that x is x of t and y is y of t. So that's basically a parametric curve as you know it from calculus. And what you can do with those things is, well, you can just basically as t varies, x of t and y of t traces out a curve, and you can pretty much presentation, which means that we've got all the tools needed to get going. First of all, we want to talk about these contours, and basically if we've got a set C of points x, y in the complex plane, remember that the point x, y is equal to the complex number x plus I, y, right? That set of points is called an arc if and only if there are continuous functions